Okay, hi everyone. Welcome to Recitation 5 today. We are going to go over Fourier series and Fourier transform. Let's begin. So, the equations you see on the screen right now are equations for Fourier series, especially for continuous signal. And what do these equations mean? The first equation, the synthesis equation, it basically said that any periodic signal, okay, with frequency omega naught can be represented as linear combination of sine and cosine of frequency omega naught as its integer multiples. So basically it say any periodic signal can be decomposed to sine and cosine function. And for the analysis equation here, it basically explains the coefficient. You see A, K here, the coefficient or weight of each complex exponential. What does it mean, complex or exponential? We're going to see in the first problem we're going to do today. And I also want to mark that A0 represent the DC. Sorry, it represent the weight or DC level. Oh, can I move it? Yeah, DC level of the signal. For example, the average signal amplitude over a cycle. Okay, so let's begin with our first problem today. All right. So the problem wants us to find the Fourier series coefficient of xt, right? And when we talk about a Fourier series coefficient, let's look back into the two equation here. When we talk about the coefficient, it actually means analysis, right? So we're gonna find AK for this question. Okay, let me write down the analysis equation. AK equal 1 over T naught integral X T E. Okay, this is analysis equation. So let's start with decomposing our signal here. The signal that we were given, xt equal 1 plus cosine omega naught t plus 4 sine 2 omega naught t plus sine 3 omega naught 3 plus pi over 6. And we were given the hint that we can use the Euler equation here. So Euler equation, basically, I use Euler equation and sign A plus B formula here. Let's look at the first term. Cos omega naught t I'm gonna use Euler equation with this chunk. So according to Euler equation, I'll get cos omega naught t as e to the j omega naught t minus, excuse me, plus e to the power of negative j omega naught t over 2. So I can write it as 1/2 e to the power of j omega naught t plus 1/2 of e to the power of negative j omega naught t. All right, that's the first term. Now let's look at the second term. 4 sine to omega naught t, right? So for 4 sine to omega naught t, if we use Euler formula with this one, it's gonna be 4 e to the power of j to omega naught 3 minus e to the power of negative j to omega naught t over 2j. All right, and I expand everything out. So in the end, I'll get 2 e j to the power 2 omega naught t minus 2 over j and minus 2 over j e to the power of negative j to omega naught t. All right. So the first two terms are rather simple. We just need to like put them using Euler formula. But the third term here, we're gonna use this equation for it. So sine A plus B equals sine A cos B plus cos A sine B. All right. Let's work on our third term here. So we have our third term as sine 3 omega t plus pi over 6, right? Sine 3 omega naught t plus pi over 6. Okay. And remember, sine A plus cos B sine A. So I'll get this term here as sine 3 omega naught 3 times cos pi over 6 plus cos 3 omega naught 3 times sine pi over 6. And we know that cos pi over 6 is root 3 over 2. And sine pi over 6 is 1 over 2. Therefore, the thing we're gonna get is root 3 over 2 of sine 3 omega naught t plus 1 over 2 cos 3 omega naught t. And now, The next step, we can put this term into Euler form. So for sine omega, sine 3 omega, not 3 here. Let's start with this one. When we put that in Euler form, we're gonna get sine 3 omega naught 3 as e to the j 3 omega naught t minus e to the negative j 3 omega naught t over 2j. And that is this first term. Now looking at the second term here, we're gonna put that in Euler form as well. So for this second term, we will have 1/2 plus 1/2 of e to the power of j 3 omega naught t plus e to the power of negative j 3 omega naught t over 2. Now we're just gonna factor in, multiply these two inside the bracket, and arrange the complex term together. So we'll have root 3 over 4j of e to the power of j 3 omega naught t minus also root 3 over 4j of e to the power of negative j 3 omega naught t. And that's for the first term. And for the second term, I'll multiply 1 over 2 in the bracket. Got 1 over 4 e to the power of j 3 omega naught t plus 1 over 4 of e to the power of negative j 3 omega naught t, right? Now I want to put the same complex term together. I want to put them together. So I can write them as bracket root 3 over 4j plus 1 over 4 times this first complex term, e to the power of j 3 omega naught t. And for the second term, I will have negative root 3 over 4j plus 1 over 4, the dual coefficient here, times the complex term e to the power of negative j 3 omega naught t. Okay, so now we got our 3 terms already. So we got this term, and this one. Let's put all of them back together. I'm gonna make a new page here. Okay, let's put all the term back together. So I'll get xt equal, okay, 1 plus cos omega t, which we use Euler formula, and we got this chunk here. Okay. And the second term for sine 2 omega naught t, we get this after using Euler formula, we get this term. And for our last term, we got this chunk here. All right. Do you have any question before I move on to the next steps? I see some chat here. Is all everybody doing okay? Please interrupt or type in chat. Oh yes, right, Jade. There's a lot of term in this problem, but we will get through this together. All right. Any question, comment, concern? Okay. Give me thumbs up if you're here. Give me some thumbs if you're okay. Thank you, Isabella. All right. So after using Euler and the sine formula, we got this term, right? Now let's compare. Oh, not there. Compare this to the synthesis equation so that we can find what are the coefficient that we need to that we are finding. Okay, so let's look at the synthesis equation. Isabella, you put terms if you're a date, okay. For synthesis equation, we have xt equal okay, so this is our synthesis equation. And on the question, it asks us to find the Fourier series coefficient. So it asks us to find AK, right? And how are we doing? How can we find AK? That is in this equation. So we need to know what should we set our K to be. So let's say if I have like A1, that means my K is 1, right? K equal 1. And my A1 is gonna be some coefficient. Yeah, some coefficient of e to the power of j 1 omega t, right? So I want to compare this term to the terms above. Okay, which is this one. And now I know that my A1, when I compare it to that one, what is my A1 gonna be? Anyone would like to try?
One half.
Thank you, Isabella. Yes, right. 1/2. Okay. Now let's try that one with a negative 1. Wait, not duplicate. Yeah, actually we can duplicate. Yeah, let's try a negative 1. A negative 1. So what is our a negative 1 gonna be in this case? I give you a hint. Look at this term. Are you okay, Isabella? Oh, yeah, it's also 1/2. Thank you so much, Isabella. Yeah, it's also 1/2. Okay. Now look at this term. Can anyone help me? What should I set my K2 in this case? Shout out or type. 2. Thank you, Jade. Is right. Now let's look at A2. Duplicate. At A2, that means our K equal to A2 e to the power of J2 omega t. Now we're gonna look at this term. Can anyone help me find the coefficient? The A2 coefficient. Shout out or put in chat. Give you hint. Oh, yes. Thank you, Isabella. It's 2 over J. Thank you. Yes. So we got our A2 as 2 over J. Great job. Let's move to the next term. This term, right? So for this term, what should my A be in this case? For this term. Anyone want to shout out? It's gonna be negative 2. Thank you so much. Yes, it's gonna be negative 2, right? So a negative 2, which means k equal negative 2, a negative 2, negative 2 j to omega t. And the coefficient that we're gonna get, what is it gonna be? 2 over j, right? And we're done with that term. Let's move to the green term. Learn how to.
Sorry.
Do you have any question?
Yeah. So what?
Oh, I see. Oh, yeah. I just see your comment. What's your question? Oh yeah. Yeah, like you say, the A0 is gonna be 1. I'm gonna show you later.
So
But I
you
think
just
kind
so you just care about the coefficient. So like for the one that you just did right now, it wouldn't be a -2/j.
Nick. Oh, thank you so much.
Yeah.
For signal prodigy. Thanks for help catching that. Yes, yes, yes.
Okay. Okay.
Cool. Thank you so much. All right. Okay, let's move to the next term. I think we kind of catch concept of how to do it now. Then let's just go quick. So for A3, that means our K is 3. And so we're gonna look at this chunk, right? So our A3 is gonna be, oh, that's a long chunk. So A3 is gonna be √3 over 4j plus 1 over 4. Cool. And another term, we have a -3 here. We want to look at a -3 for the last term. K equal -3. And you're gonna get our a -3 as -√3 over 4j plus 1 over 4. Okay. But there's one last term that I haven't covered yet, and I think some of you already pointed that out in the chat. So what about 1 here? What is gonna be the Fourier coefficient for 1? So in this case, right? If all of this chunk is gonna equal to 1, that means we don't have this term anymore, and that means our K is gonna be 0. Therefore, we're gonna start by finding A0, which means our K is 0. And therefore, we're gonna get xt. Some part of xt is gonna be A0 times e to the j0, right? Omega naught t, which is 1. And therefore, when we look at this term, we only got A1, right? Therefore, we get that A1 equal 1. A0 equal 1, sorry. And that's it. So, to sum up, we have been finding our A1, A0, A1, A minus 1, A2, A -2, A3, and A -3. And they are equal to this number that we've been finding. Okay. Do you have any question, comment, or concern for this? Give me thumbs up if you feel confident and would like to move on. Does this deconstruction only work for signals that are sinusoidal? Yeah, like Will said, it's only periodic signal. Yeah. Any periodic signal can be decomposed in sine and cosine. Cool. Any more question regarding the first problem here? Okay, if not, I'm gonna pass it over to the next person. Thank you, everyone.
All right. All right. So Alpha guided y'all through how to find the Fourier coefficients. Now we're going to examine some Fourier series properties. So this is a Fourier series properties table, and we're going to look at what happens if you take your periodic signal, x of t, and then you modify that signal. Can you get your Fourier coefficients without having to go through that whole process again? And as you can see, with each different modification, there's a corresponding change to the Fourier series coefficient. So for example, for time reversal, where you go from x of t to x of minus t, your Fourier coefficient becomes a of minus k instead of a of k. So there's all these properties, and we'll get into a few more of them with the problem, but this table is going to be your best friend. So if we're given that x of t is a periodic signal with a period of t naught is equal to 4, and Fourier coefficients is given below, where a of 0 is equal to 5 over 7, and ak is equal to 3 sine of k pi over 12 divided by 2k pi, can we use our Fourier series properties to calculate a new ak coefficient for each of these transformations for k equal to -6, -2, 0, and 2. And we're actually going to skip -2 because we got to make sure Will has time, but we'll go ahead and do -6, 0, and 2. So let me switch over to my iPad real quick. Share over here. Oh, why did that not work? All right. Sorry, give me just a moment. It's not working for some reason. Okay, I might just have to use the whiteboard or the whiteboard on my iPad. Sorry. All right, are y'all able to see now?
Yes, it's visible.
Okay, perfect, thank you. So we're given that a of 0 is equal to 5 over 7, and our a of k is equal to 3 sine of k pi over 12 divided by 2k pi. And now we want to find find the a of k coefficients for negative x with negative t, x of 4t plus 3, 7 derivative of x of t, and then e to the minus j 2 pi t x of t 4k is equal to -6, 0, and 2. All right, so the first step shoot, how do I move this screen around? Sorry. Oh, it makes me make a new page. That's not good. It's not letting me move this around, which is a bit of an issue. I don't know what's going on today. All right, we're just gonna have to make it work. Step 1 is to find our A, K values using the given equation. So I'm gonna have to go to a new page. Does it get rid of all that? It does. All right, that is fairly annoying, but we're gonna solve for A of K, where K is equal to -6. So we're going to get A of -6 is equal to 3 sine of -6 pi divided by 12 divided by 2 times -6 pi. All right, so now we can simplify this down to 3 sine of -1 pi over 2 divided by -12 pi, which is then going to simplify down to sine of -pi over 2 is equal to 1. So we're going to get, oh, that's, wait. Now I'm confusing myself, sorry. Sine of -pi over 2, yeah, is equal to -1. So we're going to get -3 over -12 pi, which is equal to 1/4 pi. So that's going to be our A of -6. Our A naught, or A0, was defined in the problem. It's 5 over 7. So that's going to remain as that. And our A2 is going to be equal to 3 sine of, we're going to get, what was the equation again? We're going to get 2 pi over 12 divided by 2 times 2 pi. So this is going to give us 3 sine of pi over 6 divided by 4 pi. Pi over 6 is equal to sine of pi over 6. I don't remember my unit circle anymore. That's equal to 1/2. So we're actually going to move that to the bottom. We're going to multiply the bottom by 2. So we're going to get 3 over 8 pi. So those are our initial A values based off of the given equation. Now we're going to solve for when our signal is transformed to negative x of negative t. So now we're going to consult the properties table, which, how do I show you all the properties table from here? I'm going to switch back and forth. Do they have easy access to a properties table on Canvas by chance? Okay. If y'all could look on the slides, I assume it's on, is that lecture 8, Fourier series? Let me take a look. If y'all could go to lecture 8, slide 14 and 15 on Canvas so that you can follow along. Under Fourier series. And I'm going to go ahead and continue, but please let me know if you're having any issues following along with the table or anything. So we have the first step when doing a problem like this should always be to identify what has been done to your signal. So in this case, we have two things. We have a time reversal and we have a amplitude scaling. Which in this case is a reflection. So on the table, we're going to find the time reversal section, which I pointed out earlier. And we're going to see for x of negative t, you get a Fourier series coefficient of a to the minus k. So for time reversal, we have signal x of minus t, and we get the coefficient a of minus k. For amplitude scaling, we actually have to look at the linearity property. Because if we remember from the past, linearity is composed of two parts. We have the additivity, and we have the homogeneity or scaling. So we can take the linearity property and see that a x of t plus b y of t gives you a of k plus b of k. So we can infer from that if we just remove the additivity, and we have this signal, a x of t, we're going to get the coefficient negative a of k. Now we combine these two properties together. And we can see with the signal, negative x of negative t, we're going to get the coefficient as negative a of negative k. Does that all make sense so far? So I haven't looked at this in a while. I believe, and correct me if I'm wrong, any of the other TAs, K is the multiple of your fundamental frequency of the sine wave and the cosine wave. Is that correct?
I think so.
Okay.
I'm looking it up right now to double check, but I'll get back to you on that in the chat. But I think so. I think Ryan's on the money with that one.
We'll
you're
double
right.
check. Okay.
The multiple.
So the K value is your function has the fundamental frequency, and your K value is the multiple of that frequency that you're evaluating at. Okay. Any other questions at this point? Okay. I'm going to continue. Just shout them out or type them in chat if you have any other questions. So now we know how to find our coefficient. We need to plug in our values of K. So we're going to plug in K is equal to -6, 0, and 2. And we know from the previous section that our new A coefficient is going to be equal to -A of -K. So, I just add an extra page, whoops. So we're going to define A prime as our new A value for this particular function, or for this particular transformation of our signal. And we're going to say A prime of -6 is going to be equal to -A of -6. So we can say that this is equal to -A6. So now we can evaluate our original function that defines A of K. We have a negative in front from this. And now we have 3 sine of 6 pi over 12 divided by 2 times 6 pi. So this is going to give us -3 sine of pi over 2 divided by 12 pi. Sine of pi over 2 is equal to 1. So we're going to get -3 over 12 pi, which means our A prime of -6 is going to be equal to -1 over 4 pi. So now we can evaluate A prime at 0. So this is going to give us -A of -0, which there's no such thing as -0. So we can just put this as -A0. And our A0 was already defined for us as 5/7. So we can just add the negative and say this is -5 over 7. Now for A prime of 2, we're going to get -A of -2. And we're going to once again use the equation. So we're going to get -3 sine of 2 pi. Oh, that should be negative. -2 pi over 12 divided by 2 times -2 pi. Sine of negative pi over 2 is going to give us -1. So, is that right? I feel like I just checked this. Sorry, that should be negative pi over 6, not pi over 2. -3 sine of negative pi over 6 over -4 pi. Sine of negative pi over 6 is going to give us -0.5. So we're once again going to multiply the bottom by 2, which is going to give us -3 over 8 pi. And because it's negative, it cancels out the -4 on the bottom, or the negative of the -4 on the bottom. And we're going to get that a prime of 2 is equal to -3 over 8 pi. Does that all make sense so far? Okay. So just as a quick recap, that is the original. So the first step we did for this is we identified the two transforms that are happening to our signal in this problem, which in this case are time reversal and amplitude scaling. And we identified the properties that we use in the table, and then we applied them to get the transformation of our coefficient. Then we plugged our values of k into the transformation of that coefficient, and we solved the equation that was defined in the problem to get our values at those k values. All right, let's move on to our second transformation of the signal.
Excuse me, how did
Yeah.
you get 8 again?
For which?
The V over 8
Yeah,
pi.
so the sine term here,
Okay.
this is equal to -1/2.
Okay.
So I
Okay.
actually just
Okay.
multiplied the bottom by -2.
Okay, got it. Thank you.
Absolutely. All right. So now we're going to move on to part B. We have x of 4t plus 3. So can anybody identify the two properties that we're going to use for this problem? Type them in chat or shout them out. Take a look at the table. You don't have to tell me the definition of them, just the name of them. Yep. So we have a time scale and a time shift present in this. So we have time scaling. So for time scaling, we get x of alpha t. Not the prettiest alpha, but it'll work out. Alpha t, alpha is greater than 0. We get a of k. And for our time shifting, we have signal x of t minus t naught gives us coefficient ak e to the minus j k omega naught T naught is equal to AK e to the minus JK 2 pi over T naught. Oh, sorry. For T naught. So we can see that with the time scaling regard, our coefficient is actually going to remain the same. We're just going to get A of K out. So we don't have to consider the time scaling. We only have to consider the time shifting. And now this coefficient looks like a mess. So how do we solve this? So we can identify our T naught value. It's going to be equal to -3 because we have a T minus T naught here, because we have a plus up here. It has to be -3 to get that plus value. So we're going to get T naught is equal to -3. And then, sorry, I'm lost myself now. We can use our T naught, our big T value we defined earlier as our period. And that was equal to 4. So now we can use this section here because our frequency here is being expanded into 2 pi over T, as frequency is equal to 2 pi over the period. So we can determine that A prime of K is going to be equal to AK e to the minus JK times 2 pi over 4, which we're going to simplify down to pi over 2, times our T naught value, which in this case is going to be -3. All right. Any questions there? The big T naught was defined in the problem statement. It is the fundamental period. So that was a given. We didn't have to solve for the big T naught. Yep, not a problem. Good to ask. All right. Let's keep going. So now we have that our A prime of K is equal to AK E. And we're going to rewrite this a little bit back into 3J K of pi over 2. So I just canceled the negative in front with the negative on the 3 and moved the 3 to the front. And now we're going to evaluate at K is equal to -6, 0, and 2. So A prime of K, or A prime of -6, is going to be A of -6 times E to the negative J, oh, sorry. It's going to be E to the 3J K pi over 2. So we can go back and see we had actually already calculated what a of minus 6 is with our original signal based off of this equation. And we got that a of minus 6 is equal to 1/4 pi. Or sorry, 1 over 4 pi. So we can come here, plug in 1 over 4 pi times e to the 3j k pi over 2.
So you don't plug in the k to
Oh.
that e to the k part?
Yes, you should. Sorry.
Oh, okay.
I was just
Sorry.
realizing I had missed that.
Yeah.
Thank you. All right, perfect. And now we can simplify this. Get 1 over 4 pi times e to the negative 18j times pi over 2. And then we can simplify it a little bit farther. That's 1/4 or 1 over 4 pi times e to the negative 9 pi j. So that's going to be our a prime negative 6 value. Now we can get a prime of 0. It's going to be a of 0 times e to the 3jk times pi over 2. And in this particular instance, we should be able to quickly identify that our k value here, when we plug in 0, is going to become e to the 0, which is just going to simplify down to 1. So we get a 0 times e to the 0, which is just going to give us a of 0, which once again we already solved for. Or sorry, it was actually a given, which is going to be 5 over 7. So a prime of 0 is going to remain the same as a of 0 at 5 over 7. And we're going to solve a prime 2. We're going to get a of 2 times e to the 3j times 2. I should be plugging it in here as well. Pi over 2. So now that is going to become a2 times e to the 3 pi j. Sorry, let me.
Hi, did it
Yeah.
voice for anyone else?
Sorry? Sorry, Ruhi, could you repeat that? Oh, did it freeze for anyone else? Or are y'all good still? Okay. I'm going to keep going. So then we know that a2 we already solved for as 3 over 8 pi. So we can plug that in. Get 3 over 8 pi times e to the 3 pi j. That is going to be our A prime 2 term. So any questions after that one? All right. So now we're going to move on to part C. And we're going to have 7 dx of t dt. So now, can anybody identify the two properties here? Yep, we have amplitude scaling and differentiation. So remember, for our amplitude scaling, we're going to use the linearity property. So we're going to have linearity, our signal ax of t goes to coefficient a of k. And then we're going to have differentiation. Or signal dx of t over dt goes to so in this case, we so we're gonna use the definition where it uses the big T as the period, as that is what we know. So in this particular instance, for those of you looking at the properties, you can see the jk of omega naught ak is equal to jk 2 pi over t ak. That once again, those are equivalent. Omega naught is equal to 2 pi over t. So in this case, we can select either one. And because we know the period, we use the one on the right. If we had been given the frequency, we would use the one on the left. Does that make sense? I don't hear any dissenters, so I'll keep going. So we're going to use jk 2 pi over t a of k. So now we can combine these two. And get a prime k is equal to a jk 2 pi over t a of k. So let's go. We know a prime of k. Oh, it's probably easier actually. We know our a value from up here. So we can actually plug that in right away. So we get 7k jk of 2 pi over t, which t is equal to 4 over 4 of k. So now we're going to get a prime of k is equal to 7 jk times 2 pi over 4 a of k. So now we're going to solve k is equal to -6, 0, and 2. So for a prime of -6, we're going to get 7jk times 2 pi over 4 times a of -6. So we're going to plug in k here. We're going to get 7j times -6 times 2 pi over 4 times, and then we have solved a of -6 before. So we know it's going to be 1 over 4 pi. So we can go ahead and plug that back in again. That's 1 over 4 pi. Now, i's are going to cancel. We're going to get 7j times -6 times, let's see, 2 over 4 times 1 over 4 is going to give us 2 over 16. Should give us 1 over 8. I did my math right, hopefully. So now we're going to get 7 times -6, just going to give us -42 times 1 over 8 times j, which is not going to give us a clean number. So I'm going to go ahead and leave it as that. Let me double check. Okay, I believe that should be correct. So we're going to get a naught of 0. It's going to be equal to 7j k 2 pi over 4 times a of 0. And now we can immediately see that we have this k term multiplied by everything else. When we plug 0 in, we're actually going to get 7j times 0 times 2 pi over 4 times a naught, or a0, which is going to give us 0. So for this case, a prime of 0 is going to be equal to 0. So now we're going to get a prime of 2 is equal to 7j k times 2 pi over 4 times a of 2. So this is going to give us 7j times 2 times 2 pi over 4 times a over 2, which we've solved for already to be 3 over 8 pi. So we can go ahead and plug that in here. 3 over 8 pi. So now once again, our pi's are going to cancel. And we're going to get, let's go ahead and cancel these terms as well. Those will all, we'll do 2 times 2 over 4, just give us 1. We can cancel all of that. We'll get 21 over 8 pi. Oh, no pi. We already canceled the pi. Apologies. 21 over 8j. Okay. Any questions there? All right. And now for part D. We're going to get e to the minus j 2 pi t x of t. So can anyone tell me what property is being used here? So it is multiplication, but it's more specific than that. This particular, oh, no, it's not multiplication. Multiplication is something else. Sorry. I didn't realize that was defined on here. So in this particular instance, we're actually using frequency shifting. Yes, perfect, Jade. So we are going to be doing frequency shifting. And for this, we once again have the omega and 2 pi over t definition. So we're going to use the 2 pi over t definition. We get e to the j m times 2 pi over t times t x of t. That is our signal. And our coefficient is going to be a of k minus m. So in this particular case, we are actually going to have to solve for something before we start plugging in numbers. So we need to figure out what this m term is because we have to shift our k value by it. So how are we going to do that? Well, what we can do is we can set our signal equal to the definition and then we can use this to solve for our m value. So we can actually cancel the x of t's and we can just solve the exponent of the e power. So we can rewrite this as negative j 2 pi of t is equal to e the j, oh, sorry, not e. We get j m 2 pi over t times t. All right, now we can divide our 2 pi over and our t over. Those will cancel. And we want to solve for m. So we're going to divide, the j over to the left side. We're going to multiply by t. So we're going to get negative j. Oh. We're going to get negative j over j times t is equal to m. Negative j over j is going to be equal to negative 1. So we're going to get negative t is equal to m. And we know from the problem definition that t is equal to 4. We're going to get m is equal to negative 4. So now we can define our a prime of k is equal to a of k minus 4 or a of k plus 4. So we have our a prime of k is equal to a k plus 4. We're going to solve for k is equal to negative 6, 0, and 2 once again. So we get a prime of -6 is equal to a -6 plus 4, which is equal to a of -2. So now we're going to go ahead and solve this. So we're going to have to consult back. We didn't solve for a of -2, so we're going to have to consult back to our defined equation, which is a k is equal to 3 sine of k pi, so in this case, -2 pi over 12 divided by 2 k pi. So this is going to give us 3 sine of -pi over 6 divided by -4 pi. The sine of the -pi over 6 is going to give us -1/2. So we can go ahead and multiply the bottom by 2. Or by, sorry, -2. We're going to get 3 over 8 pi. And that's going to be our answer for a prime of -6. Now a prime of, that's not right. A prime of 0 is equal to a of 0 plus 4, which is equal to a of 4. Once again, we have to use our equation. So 3 sine of 4 pi over 12 divided by 2 times 4 pi. That's going to give us 3 sine of pi over 3 divided by 8 pi. Using my calculator again. Sine of pi over 3 is equal to square root 3 over 2. So we're going to get 3 times square root 3 over 2 divided by 8 pi. And we can simplify that down a little bit. 2, 3 square root 3 over 16 pi. And that is going to be our a prime of 0 value. And finally, we're going to have a prime of 2, which is going to be a of 2 plus 4, or a of 6. I believe it's still no. You should, all of these values are on the unit circle, and I should know them. I just have not reviewed the unit circle in a while. So make sure you know your unit circle values, and make sure you know the Euler's formula off the top of your head, because you will need both of those on the exam. Absolutely. I know I'm setting a bad example because I'm using my calculator. Sorry. I haven't reviewed it in quite a while. All right. So we're going to get 3 sine of 6 pi over 12 divided by 2 times 6 pi. Just going to give us 3 sine pi over 2 divided by 12 pi. This one I do know is 1. So we're going to get 3 over 12 pi. Which is going to be equal to 1/4, 1 over 4 pi. And that is going to be our a prime 2 value. So, any questions on that? So those are 4 example problems using different properties. Please make sure to go back and look at these if you have any issues on the homework or anything like that. These kinds of problems. All right. Any questions on this stuff? All right. I don't see anything. Let me run through this again real quick, just kind of the process. So we solved for our original AK values utilizing our equation. And then for each transformation of the signal, we first determined what properties we needed to use and the individual effects on the coefficient. We then determined the overall change to the coefficient, and we used that to solve with our different K values. Okay. And then I don't know what we want to do for the last question, if we want to just do it next week or what, but I will pass it on. Feel free to ask any questions in chat if you still have any.
Okay, so I'm thinking we just save the Fourier transform for next week. What do you guys think, the TAs? What about the people here? Would you guys want to stay for an extra 10 minutes and listen to me talk about the Fourier transform, a little TED talk, or would you prefer to save it for next week? Are you guys' brains fried?
For 10 minutes, yeah.
10 minutes. Nick, Megan, Jocelyn, Jade. Are you guys tired, or you wanna stay? Okay, I'll do a little brief overview. I got two people.
Or
that's all I need.
we could probably do the transformations on Thursday, maybe, just in case it is coming in the exam and we have to do it. We'll probably do a Fourier transform review session or something on Thursday. What do you think?
Yeah, I'm down. I'm down. Maybe for right now, I can just give a little like 10-minute overview. No problems or anything.
Okay.
What do you think?
Okay, that's cool.
Okay, and then for any TAs who are tired, you can tap out. Okay. Can you guys hear me okay, by the way, if I talk like this?
Yeah, you're all good.
Okay, cool.
Sorry, I just realized I'm still sharing my screen. How do I end this? Okay.
Oh, there we go. Sweet.
There you are.
Can you guys see my screen and stuff?
Yep, you're all set.
Okay, sweet. Okay, so what we've been talking about this entire time, this entire past 90 minutes is called, if I can get my iPad here. Okay. It's called the Fourier series. So there's something that's a little different in the Fourier series, and that's called the Fourier transform. And they're both very similar, but they're a little different conceptually. So for the Fourier series, what you guys saw is we have a periodic signal, right? Periodic signal. And then we're able to put it through this black box, right? And output, we get a series of sines and cosines, right? Okay, and these sines and cosines can be, different amplitudes. They can be different phases, frequencies, right? And when we add these, we get back to our periodic signal, right? Now, with the Fourier transform, we're still able to quote unquote break it down into sines, but it's not exactly the case. So here we can input any signal, right? Oops. We can input any signal. So that means aperiodic or periodic, could be both. And we put it through this black box, right? And after, we're still able to quote unquote, break it down into sines and cosines, but our output is a little different. Instead, it's a continuous function showing the frequency breakdown, right? So we basically have a time domain function and what we get out is that same time frequency or time function in the frequency domain, right? Okay, so very briefly, I don't take up too much of your time, but just going over the formula really quick and just showing you how it works conceptually. We're not gonna do any problems today. So what this looks like is based on this formula. So this is a Fourier transform, right? So here we have our time frequency function, our frequency continuous function showing the frequency breakdown, right, in frequency domain, shown here. And how we get that, taking the integral of our initial time domain signal with this. So you may wonder, okay, what does this actually mean? So first, I'm going to show you what that looks like. So let's say we have this arbitrary signal, right? And this is how it works in the real world. Like you're gonna measure some signal, and you're gonna want to know about the frequency breakdown of it, right? So you're gonna measure something. Let's just say voltage. Okay, let's say it's a biopotential. You're gonna measure something. It's gonna look all weird. It's not gonna be periodic because it's very rare you're gonna measure something in the real world and it's gonna be periodic. It might be. It's like ECG or something, but it might not be, right? So what we can do is we can overlay a function of a known frequency. So this is us. We're deciding this frequency, right? We decide this frequency. This is known. This is like on MATLAB, right? And what we're able to do is we can map the similarity between this known frequency and our original signal. So here, frequency and similarity, right? And so let's say this, mapping, with this certain frequency, let's say that's the value, just some bar chart. If we want to say, I don't know, 5 hertz, I don't know, random value. Okay, and now let's do a different frequency. We can do a faster frequency, right? So that's going to be somewhere over here. And let's say, some other value, I don't know, 60 hertz, I don't know, any random value, right? And so what we can do is we can form a continuous function that shows the frequency layout of this original signal. So we could get something like this. And please interrupt me if you have any questions. If I'm spitting out nonsense, I would like to know from you guys if you don't understand. So it could just look something like this, right? We can get a bunch of bins and we can connect the dots, right? But the last thing I want to go over quickly is how we actually get this from the formula. So I think it's important that you guys look at this formula and you don't just turn off your brain and follow the formula. It's kind of important to, in my opinion, to understand like where these things come from and similarity, like how do we even get this? Okay, so here's what we get. We get this continuous function. We got that over here. And we're taking the integral. Okay, cool. Our initial time domain signal. Okay, cool. And then we get this e to the minus jwt. So what is that all about, right? So this is a little Euler shenanigans, right? So if we want to, map this, right? So this is this, and what that looks like here, we can show this here. So our y-axis is the imaginary, right? And the real is just the real values. So we can measure some value, right? So we would be able to decide this frequency, right? It'd be something like this. And here we have cosine. I don't want to do any proofs or anything. I would honestly I would fumble the proofs so hard anyways. So here I'm just showing you this is how we get these sines and cosines. This is how we get these frequencies. This is the Euler. So we look at this. This is how we get the frequency, right? There's the W. There's our angular frequency, right? And so how we're able to get the similarity is by cycling through these different frequencies and almost doing convolution. We are actually doing convolution in a way, right? This negative here is us flipping the signal, right? So here we're able to find the similarity between, if you want to pretend that this is a perfectly periodic signal that we determined, we're able to find, convolve that with our initial signal to find the similarity between this known frequency and our initial signal. And that's how we're able to get the frequency mapping, a continuous function for all these different frequencies of our initial signal, right? So we could just loop through frequencies. And so a lot of this you might remember from convolution, right? The integral, here's us time reversing, right? So it's not exactly convolution, but it's a little like convolution, right? Okay. Any questions, guys? So all in all, Fourier series, we have a periodic signal. We input that. It has to be periodic. It's a requirement, right? How are you going to add a bunch of periodic things and get an output of something like that's not periodic? Just intuitively, it doesn't make sense, right? So you input a periodic signal and you get a series of sines and cosines. And they can be different amplitudes, phase, frequencies. You add them, you're going to get your initial signal, okay? The Fourier transform, we're still able to, quote unquote, break it into sines and cosines, but our output is not the same. We don't get an output of sines and cosines here. Our output here is sines and cosines, a bunch of different functions. Our output here is a single function that is able to tell us the frequency content of this initial signal, our initial inputted values, right? And that's useful in a lot of ways, right? A lot of times you're interested in the frequency content of your signal. Because if it's maybe it's EEG data, that all the different frequencies could have different cognitive functions. If you're filtering your signal somehow, maybe you want to check your filtering is working the way you intended it to, or you have some noise in your data. You want to know which frequency the noise is coming from so you can filter it out, right? There's a ton of applications for Fourier transform. Okay? Does everybody feel pretty good about that, or did I fumble? You guys understand? Let's get a sea of thumbs up, guys. And so you're going to hear a lot about the domains, right? So here we're in the time domain. And by doing the Fourier transform, we get into the frequency domain, right? And I didn't talk about it, and we'll go over it next lecture, next recitation. But we can actually do the inverse Fourier transform. We can take a frequency domain signal and go backwards to get our time domain signal. Okay, I hope that made sense. If it didn't, don't worry, we're gonna say it 50 times. I don't think anybody's ever understood this on their first time. So if you guys did, I'm very impressed. So I promise practice makes perfect, and just do your best and ask questions when you're confused and do as much practice as you can and watch YouTube videos, and you're gonna be fine. Okay? Everyone feeling good?
I also want to say just real quick before we end this, I believe the TAs are going to coordinate a review session sometime this weekend. So we'll send out an announcement once we know what time we're going to do it. And we'll make sure we record it as well. So if you can't make it, you can watch it back. So just keep an eye out for that.
Okay, sweet.